Okay, in this video we're going to be looking at the notes for 5D and 5E. So we're going to start with 5D, and that's going to be the conservation of energy. So when energy is conserved, or sorry, not when energy is conserved, energy is conserved, and that means it cannot be created or destroyed. So you can't create energy, you also can't destroy it, but what you can do is sometimes it can be transferred into or out of a system. And a system is an object, or it could be a group of objects that you're looking at. So the next thing is the conservation of energy, or the conservation of energy equation. And what that is that describes the flow of energy in a system. This is it right here, that's the equation. And again, there's a lot of terms, we're going to go through each one. But what this equation's for is basically if you have a system, so let's say we take a block on a spring. So again, the block's on the spring, and then at some later point in time, the block is pushed off of the spring and it goes in the air. You could say this is a system. And again, we're interested in seeing how that energy is being transferred, how energy changes, or how energy in the system is changing over time. So we'd look at those 2 points, and this equation is actually going to help us analyze in more detail what's happening here. So we're going to go through each term. The first is work, W. That work is the flow of energy into or out of a system. So again, if you had some, I don't know, additional source of energy that flowed into the block or the spring, you'd say work is being done. But for these two sections of the notes, we're just going to say work is 0 joules. We'll come back to it later, but for right now, we're going to say it's 0. The next one is Ki, so that's the initial kinetic energy. So that's the kinetic energy before any energy transformations. So again, energy transformation is typically you examine the system at 2 distinct points in time and then see how energy changed. The Ki, so that's if there's any kinetic energy in the first part of the system. And again, there doesn't always have to be, but if there is, you'd put a number in here. The next one is Ui. That's the initial potential energy of the system. Again, keep in mind that there's different types of potential energy. There's Ug for gravitational potential, there's Uc for potential chemical, there's Ue for potential elastic, and so on. So again, this is sum of all types of potential energy before an energy transformation. So again, there could be multiple different types of potential energy. The next one is Kf. That's the final kinetic energy. So that's the after the energy transformation, is there kinetic energy? If so, you'd put that in here. Like for example, this drawing with the spring, the block is moving, or the block in the spring. In part 2, the block's actually moving up here. So you would say that, yeah, there is some final kinetic energy. And last one is the final potential energy of the system. That's the sum of all types of potential energy after the energy transformation. So at the end of the time you're looking at, is there any type of potential energy? So that's the conservation of energy, the equation. We're going to look a little bit more about how it's applied to a problem. Okay, here we go. So again, we have the equation. Now we're going to look at, maybe a little bit what it would look like in a problem, and then you're going to see an example out. So when you're solving a conservation of energy problem, it's important to use these strategies. So the first one would be to write out your knowns and unknowns, like if you know the mass, or if you know the gravitational potential energy. That's all good information to write down before you do anything. Next thing would be to draw a picture, like right here would be helpful if you're not given one, to draw out what's happening. The next two would be to determine what is your initial point in time and what's your final point in time. So again, your initial point in time would be before some energy transfer or transformation happens. Like if you have this slope, a good initial point would be on the top of the slope while it's sitting there. A good final point would be maybe if you looked at the block down here, because something's happening between these 2 points. It's falling, energy is being transferred. So final point would be after some kind of energy transformation takes place. The next thing is to determine what types of energy are in the problem in both the initial and final points. So what type of energy is here at the initial point, what type of energy is in the final point. And then the last thing is to plug into the conservation of energy equation and to solve. And we're going to see an example real shortly. But that's the idea, to write out your knowns, to draw a picture, to determine where are two good points in time to look at, and to determine what types of energy are present, and then to really plug in the last one, just doing the math out to solve for what you want to solve for. Okay, now we're going to see a problem of this. Again, I know it's a lot of stuff. It'll be a little bit simpler once you see a problem. Okay, so this is a good example problem of the conservation of energy. So again, before I go through it, make sure you're taking an attempt at solving it. Again, solving it, not reviewing restaurants on Yelp, solving it. Okay, so we'll see this problem out. So what we have here is we have a box, 3 kilogram box sitting on the top of a frictionless ramp, 2 meters tall. Behind the box there's a spring with 100 joules of stored energy. The spring pushes the box down the ramp. How fast will the box be moving at the bottom? So let's draw this out, that's probably helpful. I'll draw it right here. So we have as a slope, a ramp of some kind. We have a block that's sitting at the top of the ramp, and then we have a spring that's behind it that's storing energy. And then what's happening is it's being basically shot down the ramp, and it's going to be moving at some speed at the bottom. So again, we'd like to see, we're ultimately trying to figure out how fast is it going to be going at the bottom. So if we knew its velocity, and we know what the box's mass is, we know the height of the box initially, that it was on the ground, off the ground. We know that there's elastic potential energy, or 100 joules of it stored in the spring. So again, to do this, we have a picture. We got our knowns and unknowns. The next thing would be to think about where would be a good initial and final point. So if we're looking, if we want to figure out the final speed, it's probably a good idea to look at the bottom of the ramp. That'd be a good point. And then it's probably also a good idea to look at the box at the top of the ramp where we have some information. Like we have some information about the spring. We know how high it was at the top. So those would be good 2 points to look at. And then would be a good idea to write out the conservation of energy equation, and then we could think about what types of energy are actually present. So again, the equation, work plus all the initial kinetic energy plus all the initial potential energy plus the final kinetic energy plus all of the final potential energy. So before we start plugging in, we're going to look at it and see if there's stuff we can get rid of to make this equation a little simpler. We can get rid of work because there's not going to be any energy transfer in these problems just yet. Again, there's not anything in the problem to indicate that more energy is being transferred in or out of the system. So we're going to say that's 0 for now. There's no initial kinetic energy because the box isn't moving at the top. There's a spring behind it, but did not say it was moving. There's initial potential energy though. There's actually two kinds. So there's going to be a potential elastic energy because of the spring behind the box, and then there's also going to be some initial gravitational because the box is raised off the ground. So again, there's two types of this potential energy transferred into two different types, or there's two different types of potential energy at the beginning. Then at the bottom of the ramp, there's really no potential energy at the bottom. It's pretty much on the ground. There's no elastic anymore either because the spring has already shot all the energy into the box. But there is kinetic. It is moving at the bottom. So the next thing would be to see if we can simplify this a little more. And we can. We have formulas for potential gravitational and kinetic. And we know what potential elastic is, what the number is. So we're going to write that out. UE plus mgh, the formula for gravitational potential energy, plus the formula for kinetic energy. And then we're going to plug in. So we're going to plug into each thing. So again, once you hit this point, it's all just algebra and plugging in. The physics part is being able to get to here. So what we have is UE, that's 10 joules, plus the mass, 3, the acceleration due to gravity, we'd assume this is on Earth, 9.8. The height is 2. It's equal to 1/2 times the mass, again, 3, times the velocity. We don't know that. So we're trying to solve for velocity. So we're going to get, if we plug this in, if we do the math out, we're going to 158.8 is equal to 1.5 v squared. And then that comes out to 105.86 repeating is equal to v squared. So we're going to get v, the velocity, is going to be 10.3 meters a second. So again, with this problem, it was you had to utilize all the kind of strategies, drawing a picture, looking at your knowns and unknowns, thinking about what types of energy were present, crossing out ones that weren't there, and then plugging in, doing a little bit of math at the end. So again, that's a good example of the problem. Make sure you have it down, make sure your notes are notated, and that's it for now.